recording. Okay, so the first thing I do when I look at a question like this is I just recognize some stuff, right? And hopefully you've been doing this for long enough that you can recognize some stuff too. So the first thing that I recognize is that if I have four diodes that look like this, and I've got an AC input symbol over here, then this is a bridge rectifier. So I'm looking at this. I'm also seeing a capacitor over here, and that looks familiar to being in a bridge rectifier. And then there's some other bits and pieces that I recognize. So this is an NPN transistor, for example. This is, we looked at yesterday, that's a Zener diode. If you didn't know what a Zener diode was, at least you could recognize it as just a diode. This is a resistor. This is a resistor as well, and this one just says RL, so that's our load. So we know this is some sort of bridge rectifier. Now, this is one of those questions that asks you, hey, can you look at a schematic and can you draw that on a PCB? And they're pretty generous in terms of making the schematic and the PCB pretty close to one another in terms of their layout. And they've also told you that it's missing 11 missing connections. Now, the connections are, if we think about connections, I'm sort of thinking about the places where you can actually mount components. And what we're looking at here is we're looking at the strips of copper, and here are the little holes for components. And so it's asking you to draw the missing connections. It's not asking you to draw the components. But if you draw the components, it can help you out a whole bunch. So that's something that you can keep in mind. I would, with me in an exam, have a grey lead pencil, one that's reliable, right? That means having a sharpener or having a mechanical pencil with leads, and also having, pens and, if you like, fine liners and things like that, so that you can work in sort of, an impermanent and then permanent way. Because I'd start this in pencil, and I'd think to myself, okay, so the diodes probably go in here, right? And we can see we've got a spot here, we've got all these different places to put the diodes. So I'm probably not going to worry about the diodes, but you could draw those in if you wanted to. But I'm going to start with the capacitor. And I know the capacitor is going to go somewhere in here. And I'm just going to draw circuit symbols. So there's my capacitor. And so I need a hole. I didn't mean to change to black there. I need a hole here and a hole here for my capacitor. Now, if you drew your hole up here and up here, you'd still probably get the marks for it, right? Because you could stretch the legs of the capacitor right over there. But it's probably a little bit more appropriate to draw them where I've drawn them. And then this is going to go down here like this. And this is going to go up here like this. And join into that. So there's the spot for your capacitor. And then the next thing that you encounter working along the circuit is you encounter this resistor. And so what you could do is you could put another, or draw the resistor in like that. And then, we need a hole for the resistor and a hole over here. And then we can fill in this bit like this. And next component working along the line is this transistor. And we could draw, we can draw the symbol for our transistor if we like. And so we need 1, 2, and you could either draw the hole down here like this, right, for a transistor where the legs are offset, or if you wanted to, you could draw the legs over here like this, where they're all in a line. I might draw them offset, just because, well, there's two reasons. I assume if there's a transistor built into this power supply, or sorry, this voltage, this bridge rectifier and voltage regulator, I assume that if there's a transistor built into it, it's kind of a beefy transistor. And the beefy transistors tend to have offset legs. It's not really very important at all that you know that, because like I said, either would be fine. You get a mark for it. So there's my spot for the transistor. And then this resistor has to join onto the base of this transistor. So we need a track that goes from the resistor to the base of the transistor. And then how you work along the circuit is completely fine. You could work along to your load, or you could work from this point here. I'm going to work actually from this point here where the diode is, not for any particular reason, just cause. So here's my diode. And so for my diode, I need a hole here and a hole here. And that has to join this track here and then come over here. And the diode just joins back up to this point where our capacitor is anchored to. So we complete this track here. And the last thing we got is this resistor over here, all by its onesie. So here's our resistor. We need a hole there and a hole there, and we need to connect those. And let's just count it up. So it said we had 11 missing connections, so let's have a quick look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's our 11 missing connections. And so we're in the clear. So you don't get marks for drawing in these components. But what they do let you do is, I think, really sort of successfully be able to build this sort of strip, this PCB, and all these traces and all these connections in like a clever way. And you can also check your work, and you can move along really systematically. And so I do encourage you, take a pencil into the exam with you. Pencils are great. All right, so now that we've done that, let's look at some of the sort of meat and potatoes marks here. So this question in total was worth 9 marks, which is a huge number of marks in an exam that's only worth, I think off the top of my head, it's worth 80 marks, but I could be making that up completely. Right, so let's have a look at the information that we've got. We've got some values. We know that our voltage supply is 24 volts. We know that we've got a capacitor, and it is a 100 microfarad capacitor at 5 volts, so it's rated for 5 volts and 100 microfarads. We know that resistor 1 is 50 kilo ohms or 50,000 ohms, and our resistive load, or RL, is 300 ohms. Whenever they give you data, guys, it's a good idea to go through and underline it or highlight it. Just read it. It's important, right? They haven't put it there for no reason. You can guarantee they put it there for a reason. And then we've got some information here, and that is the current voltage graph of our particular Zener diode that we're looking at here. So, in other words, this is our IZ minimum right here. This is our IZ max right here. Now, you don't need to know that this is our IZ min and our IZ max. You just need to be able to look at this graph and go, okay, this is voltage on the x-axis. This is current on the y-axis. When we have this much current, we have this much voltage. And that's, this is, because these numbers are negative, this is the reverse bias direction of that diode. So this diode's reverse biased. This is the bit we care about. Now, here's some easy marks, or some fairly free marks. Let me just change the size of this pen. All right, so this is a bridge rectifier and voltage regulator. Now, I'm drawing from memory here, but I think If you said it was a bridge rectifier or if you said it was a voltage regulator, the examiners awarded you a mark because it's both. But, for safety's sake, I'd say it's both because we know this is a bridge rectifier. And you should also know, I hope from this lesson on Zener diodes, that Zener diodes are really used as voltage regulators. They have other cool uses, but the ones that you're going to know about at this stage, they're all about voltage regulation. So if you're not 100% sure and you see a question like this, think to yourself, what does the component normally do? It's like when you see an NPN transistor. Even if you can't figure out exactly what it's doing in the circuit, it's probably a switch, right? Because that's what we like to use NPN transistors for in the systems engineering exams. Okay, so what's the expected reading of the voltmeter? So there's a voltmeter over here, and to figure out what the expected reading is of the voltmeter, we really just need to ask ourselves, okay, so what does a Zener diode do? It regulates voltage, and the way that it works is that everything that is in parallel with the Zener diode, and even though there's a transistor here, this part of the circuit is still in parallel with the Zener diode. It should be the same voltage that the Zener diode is. And the Zener diode, is rated for, what's it rated for? It's over here on this information, right? So if it's conducting properly, it should be 10 volts. Now, lots of people got that question wrong. And if you got that question wrong, don't freak out, because like I said, it's only worth 1 mark, and people don't tend to do super well on these exam questions. And so dropping a few marks here and there is okay, but throughout your revision process, do try and get yourself to the point where you're getting as many questions right as you can. All right, here's the part where we actually need to do some real thinking. All right, so it's doing what's really common in these style of questions, and it's saying that something happened that what you were expecting. Why did that happen? And just before I, go through that question, if you didn't know the answer to this question, and then you got to here, where it said that the voltage was 5 volts, and then it says identify the mistake in the design, right? Look at this. It's telling you that 5 volts is a mistake. So if you wrote 5 volts in there, it's probably not quite right. Now, if you looked at this and were like, wow, 5 volts, I don't understand. What? Huh? What? Have a look at your graph, right? There is something here that says a 5. They put that in the exam for a reason. And so even if you didn't know that this was supposed to be 10 volts, looking through the question and trying to get inside the person who writes the exam's head, you can look at this and go, okay, that's 5 volts, that's 10 volts. It's probably supposed to do 10 volts. All right. So identify the mistake in the design of the circuit that led to the reading and show your working. So looking at, and I might just erase some of this stuff. Looking at this graph here. Now, we know that a Zener diode controls your voltage, but it requires a certain amount of current in order to do so. Now, if we're not conducting, if the diode is not conducting at its proper operating voltage, look here, it's conducting at 5 volts. What's going on in this part of the graph? Well, in this part of the graph, this little point right here, we can see that we're not quite at the current that we're supposed to be at. Now, if you remember that that's IZ min or not is actually irrelevant. But what's important is that you can look at this graph and go, okay, this is the point where things are supposed to work the way they're supposed to. Here's the point where we're not quite there, right? And look at all this, this stuff up here. R1 is a 50,000 ohm resistor. That's a huge resistor. That's pretty big, right? So looking at this, if we think about current pathways, current pathway, fairly good chance that this resistor is just limiting current so much that it's actually stopping our diode from working properly. So you could write something like um, Zener Diode current is too low to let's say supply 10 volts, and they're asking you to show you're working. And if you're ever asked to show you're working, you're probably being asked to use Ohm's law. So V equals I R. Now, what do we know? We know voltage is 24 volts. We know that our resistance is 50,000 ohms, and current is our question. And so we should know that our current is equal to our voltage divided by our resistance, which is 24 volts divided by 50,000 ohms. And if we plug that into a calculator, because I can't do that in my head, divided by, oh, that's wrong, divided by 50,000, we get 0.00048 amps, which is, that's not even 1 milliamp, right? That's a bit less than half a milliamp. And we know that we need at least a milliamp to get this sucker to conduct. So this is the amount of information that you need to get all of these marks, right? So just identify why it's not working the way it should, and then use Ohm's law to sort of demonstrate why that is. 95% of the time, if you need to do any maths on these big circuit questions, it's just using Ohm's law, right? You may have to have like figure out the equivalent resistance or something like that first, but it's usually Ohm's law. All right, great. So having figured out this, this question up here is pretty straightforward. So if the resistor is limiting current, then you just change the resistor value. And in this case, let's do the maths first. So in this situation, current is equal to, well, we need 1 milliamp. So that's 0.001 amp. That's the current that we need, the minimum current that we need. Let's put I min and let's just call it I middle. And let's say that we want, we actually want 0.05 amps. So that would be 5 milliamps, which puts us in the nice, safe middle zone. So this is what we're working for. And so now we just need to use Ohm's law to solve for the resistor in this case. So resistance is equal to voltage divided by current. And we know that our voltage is 24 volts. And we know that the current that we're looking for is 0.05 amps. And then we do that maths. And we come up with a resistor value of 4,800 ohms. And there's your working. So for the what is it, replace